Yeah, it's done. I uploaded the final version. Okay, so linear programming. This weekend we'll have a Zoom, and it will be on linear programming. Okay, so and other questions too. Okay, so these are the topics, and so they're actually a canonical form and a separate standard form of linear programming. I think the lecture notes I have put down the standard form too, but here we'll just do the canonical form of linear programming. And there's a MATLAB has its own format too. It allows lower bounds, upper bounds, and separate equality constraints. Anyway, so this is what a linear programming looks like in canonical form. Minimize C transpose X subject to AX greater than equal to B. I know you guys are used to less than equal to 0, but this is the canonical form and universally accepted. So that's what we'll follow for just linear programming. And X is greater than equal to 0. AX is greater than equal to B, and X is greater than equal to 0. These are the constraints. Okay, now this X is in n dimensions. So we have n primal variables, n scalar primal variables, xi, I equals 1 through n, and we have m constraints. Okay, so we also have, by the way, for each scalar primal variable xi, we have xi greater than or equal to 0. So we have n constraints here corresponding to these. And then we have m constraints here. Each row of ax greater than or equal to b, you can read off a row. The left side will be this. Aij is are the entries of this matrix A in row I and column J, and Xj, you know, it's jth element of X, and likewise Bi. Okay, so this is the ith row of this vector constraint, Ax greater than or equal to B. Okay, and A is an M by N matrix. So we have another M constraints here. So the total number of constraints is M plus N. Okay, and we are operating in N dimensions because X is N dimensions. Okay, so these are the sizes of the vectors and matrices. Okay, so now the feasible region is a convex polytope. This. So each row of this Aij equals Bi, summation Aij equals Bi is one of these. Okay, each of these straight lines here, but they will be n minus 1 dimensional planes in general when this is n dimensions. Okay, and then you would have xi greater than 0. Here we have just 2, right? So we have, it should lie in the first orthant. Okay, the x must lie in the first orthant. So we have these n constraints, one along each axis. It cannot cross over to the other side. So we have constraints here. These are m constraints. And then we have n constraints, xi, greater than or equal to 0. Okay, so now every corner of this is formed by the intersection of n hyperplanes. N hyperplanes, okay? And so we have how many hyperplanes, including these? We have m plus n hyperplanes, correct? And so m plus n choose n will be the total number of corners like this, including the origin. Okay. Now, two observations. The feasible region is convex. If you're surrounded by straight lines, it cannot be concave. You cannot have any concave part. Okay. So this region is, the feasible region is convex, and it's surrounded by all these hyperplanes, n-1 dimensional hyperplanes. And now, these are the contours. C transpose X, the objective function, this one, C transpose X, okay, equals some value, another value. So, and since this is linear, C transpose X, so it will be constantly increasing, right? They will all be straight lines. C transpose X equals alpha 1, C transpose X equals alpha 2, C transpose X equals alpha 3, and so on. Maybe it's being minimized along this direction. And so this would be the optimum solution, the red dot, the minimum. Okay, sorry, it says maximum here, it's the minimum. Okay, so that's the minimum. It will always be one of these corner points. Okay, so this is a combinatorial explosion if you just randomly look for all intersections, all these corners. Okay, so the original simplex algorithm was developed right after World War II because linear programming was very important in the World War. Okay, so this is the capacity I have, and then shipped to dispatch here or here, loaded with this many tanks or this much fuel, whatever. Okay, so linear programming was very important, and that's why it was developed. Only in the 90s, late 80s or early 90s, I don't remember. No, it was 90s, that an interior point method was developed. So you start from the interior, and then you gradually migrate to a corner. Okay, but before that, what the simplex algorithm did was it was jumping from one point to another until it wouldn't be able to minimize any further. That was the original simplex algorithm. That's just a little history of linear programming. So the solution, if it exists, is unique, and it's in the corner of this feasible polytope.
Is it in 2 dimensions?
No, it's in n dimensions. Here I'm illustrating it in 2 dimensions. So we have x1 and x2 axes, but in general we have n axes, right? So that's why we have all these. Okay. You understand how I got this m plus n choose n. Each intersection, each corner would be defined by the intersection of n hyperplanes. Okay, in 2 dimensions, so each corner is defined by the intersection of 2 hyperplanes, right? In 3 dimensions, think of 3 dimensions, each hyperplane. So if you have 2 planes, the intersection would be a straight line. So you have to have 3 planes intersecting to define a point, correct? And so in 3 dimensions, you need 3 planes, and you can extrapolate. So in general, you need n hyperplanes to intersect. And how many hyperplanes do we have in all? M plus n, because that's the total number of constraints. Okay, and so that's why I get m plus n choose n. And so this is a ridiculously large number when n is 500 or 1,000 or 10,000 dimensions, and m is again another couple of thousand more. Okay, so the simplex algorithm still is an excellent approach for most practical problems, but there is the Karmatkar algorithm and extensions of that, which is based on interior point.
But so we have 2 unknown variables, so we can do that in 2 dimensions.
This is for x1 and x2.
Yeah, but why do we need multi-dimensional plane?
Well, because I just told you that x is in n dimensions. Okay, so it's not just 2 dimensions. Okay, we're not in high school, so we are looking at n dimensions. So this is there are 2 kinds of degenerate cases. This is unbounded solution. So this is, you see, the feasible region is unbounded; it stretches to infinite. Okay, and so this is one case, a degenerate case. And this is another degenerate case. There is no x that can satisfy all the constraints. Okay, these are 2 degenerate cases of linear programming. Okay, now, I don't remember quite well, but if the standard form of linear programming has an equality constraint, but what we'll do is, suppose we have equality constraints. How do we convert them to this form? Inequality constraints. And conversely, if we have inequality constraints and for some reason we want to convert them to equality constraints, how do we do that? Okay, so that's very trivial. So suppose I have one equality constraint of this form, A transpose X equals B. Okay. So this is, as a summation, this is what I write. Okay, I have a constraint like this. So what I can do is, one approach is variable elimination. I pick one variable xj such that the corresponding aj is not equal to 0. Okay, and then from this equality, I see that xj equals b minus 1 over aj times the summation ai xi, correct? For all I not equal to j. The summation excludes xj because I'm trying to express xj in terms of the other x's. Okay, and then what we do is this, I get an expression for xj, and so I use this expression and I can replace xj in the objective function and in the other constraints as well. Okay, so this way I'm eliminating xj altogether from the optimization process. Okay, and then the other option is this. So I have this, A transpose X equals B. I take this equality constraint and I convert it into 2 inequality constraints. A transpose X is less than equal to B and A transpose X is greater than equal to B, which is the same thing as negative A transpose X is less than equal to negative B. Right? So these are the 2. I take one equality constraint and convert it into 2 inequality constraints, and they're opposite. So obviously these 2 would be satisfied only when A transpose X equals B. Clear? Okay. Now, from inequality constraint to equality constraint, how can we do that? So suppose I'm given this, A transpose X less than equal to B. Now, for some reason, I want to convert this to an equality constraint. How do we do that? I introduce a new variable, xs, a slack variable. Okay, and then I write this inequality will be replaced with A transpose X plus X is equals B, where xs is greater than equal to 0. Okay, so this is another way to constraint reformulation. So here you are converting an inequality constraint to an equality constraint. Now, you might have a case where, why do I need to be in the first orthant? All the xi's must be greater than equal to 0. Suppose I have an unrestricted variable, something that that can be negative too. Okay, in that case, what do? I let x be equal to xa minus xb. I replace x with xa minus xb everywhere with xa and xb greater than or equal to 0. Okay, so this is how you handle the constraints. Here are applications. Okay, this is probably, historically, this would have been very important. Max flow. Okay, this, I'll just going to give you just brief ideas of different applications. So this max flow is like this. You have a weighted digraph. Okay, the nodes 1, 2, 3, 4, 5, 6, they are like, maybe think of it as a flow of water or something, and each of these is a connection. That's all. No way to store water or something. Okay, so water flows in these direction, and these weights are the capacities. So 1.5 gallons of water can flow from node 2 to node 3. Okay, and between 3 and 4, 2.3 gallons can flow up to 2.3 gallons between 3 and 4, but you see arrows point both ways, so they can go either way. And we have a designated node called the source and another designated node called the destination. And so from source to destination, we want to maximize the flow. So how will we direct how much water will go from here to here, from here to here, from here to here, and so on? That's what we want to find. Okay, you can kind of see how it would help in war. Okay, there's another issue. Anyway, I'll talk about it just in a minute. So what we want to do is, how do we try to maximize? So xij is the flow from node I to node j. Node 1 to node 2, this is x1 to node 4 to node 5 would be x4, 5, and so on. So we want to maximize the flow. So we can either look at the source x12 plus x14 would be the one that we maximize. Or alternately, we could maximize x36 plus x56, the inflow to the destination instead of the outflow from the source, right? So we can choose to maximize either these two or these two, same thing. Okay, so this is our objective function. I choose the outflow from the source. x12 plus x14 is what I want to maximize. Subject to, these are a set of constraints. 1 to 2, the flow cannot be more than 1.2, right? So x12 is less than or equal to 1.2. x2 to 3 cannot exceed, x23 cannot exceed 1.5. So whereas x23 cannot exceed 1.5. Okay, so these are one set of constraints. There are another set of constraints. For each node, okay, excluding the source and the destination, for all the other intermediate nodes, the inflow should equal the outflow. None of these intermediate nodes, 2, 3, 4, and 5, have the capacity to store water, or they don't carry water, a lot of water either. Okay, so the inflow must equal the outflow. So let's consider 2. Okay, so what's the total inflow? x12 plus x42. x12 plus x42 should be equal to the outflow. Outflow is x23 plus x24. Okay, and likewise, for each of these 4 nodes, I have another 4 set of equality constraints. So I have inequality constraints and equality constraints. And of course, the flow must be positive. So all these variables are positive. or greater than equal to 0, non-negative. Okay. These are called the capacity constraints. How many capacity constraints do I have? Number of edges, right? Including 2 ways. So count this as 2. This is like 2 edges. Okay. And they are inequality constraints. These are capacity constraints. And these are equality constraints, the flow constraints. How many flow constraints do I have? The number of intermediate edges, excluding the source and the destination. Okay, so that's how we do max flow. We can formulate a max flow problem in terms of linear programming quite easily. Fractional programming. Now, this is going to be a little more complicated. Okay, this is the problem. We want to minimize C transpose X plus D. D is a scalar divided by P transpose X plus Q. Q is a scalar. Okay, subject to AX is greater than equal to B. Now the denominator obviously has to be greater than, it cannot be 0. Okay, so that's why I have a greater than 0 instead of a greater than equal to 0. And X is greater than equal to 0. So this is my fractional programming problem. This can be readily converted to linear programming, miraculously, okay, by change of variables. So just 1 over P transpose X plus Q, the denominator part. So this is this scalar variable Z. And Y is X divided by the denominator. Just X divided by this denominator. And since this is Z, X divided by the denominator is Z of X, Z times X. Correct? Okay. So this objective function becomes C transpose Y plus DZ. C transpose Y plus DZ, correct? The denominator part is Z, and Y includes the denominator here. So C transpose X divided by denominator is this. How do I get to this? This inequality here is I simply, since I know that P transpose X plus Q is greater than 0, it must be, otherwise this would become infinite, right? So because of this, it's positive. Therefore, I can divide both sides by the same denominator here. So AX divided by this denominator greater than or equal to B divided by this denominator. Okay, and then you can make the replacement. You can do the replacements here. AX divided by denominator is Y. And here you would have B divided by the denominator. This is Z, so this is BZ. Okay, and of course, Z must be greater than 0. This is Z. Since P transpose X plus Q is greater than 0, Z must be greater than 0. And likewise, X is greater than or equal to 0, so Y also must be greater than or equal to 0. And so this becomes our linear program. It has these variables, Y and Z. Okay. And so once you solve it, like you cannot impose strictly greater than, right? It has to be greater than or equal to. That's what we're used to. So what can be done is if you reach Z equals 0, then it's an invalid solution. Maybe you should have another restriction. Z is greater than equal to epsilon or something to get another solution. Okay, you shouldn't get Z equals 0 as the solution. So once you get Y and Z, then you can, from Z, you can get the denominator, and then from Y, you can easily get X, right? And once you get X, well, you know what Z is. Z is there, and so you get your X from here, from Y and Okay. Or you can just say x equals y divided by z. So this is fractional programming. L1 norm minimization. So this is actually in your homework. Okay. So this is L1 norm minimization. This is my problem. I want to minimize no constraints. I just want to minimize this. One norm of ax minus b. Okay. Now you know that ax minus b is a vector, a column vector. Okay. So what is the one norm? It's you take the absolute values of all the elements and add them up together. Right? So let the ith element, absolute value of the ith element be this, yi. This is, I'm introducing a notation here, the ith element of ax minus b, and this means it's the absolute value. Okay. So since it's an absolute value, yi must be greater than or equal to 0. Correct? So this is the ith element, and this is the absolute value of the ith element is yi. So what's the objective function? Summation I of this, the absolute values of all the elements. Right? And since that's yi, so it's summation I summed over all i's. Right? Oh. That's the L1 norm. So here is how I formulate my linear programming. So this is my original problem. I have to minimize this. This is summation of the yi's, correct? Which is the same thing as 1 transpose y, vector y. You see that? And y must be greater than or equal to 0, so I have a constraint here. Now, yi is the absolute value, right? So let's say yi is 5. The absolute value is 5. That means that ax minus b, the ith element of that vector, is either 5 or minus 5. Correct? So we have this situation here. I'll explain that in a bit. So let's look at this figure. I have a minus yi here and a yi plus yi here. And right in the middle is the origin. I haven't shown the origin, but that's in the middle. Okay? And so minimize this 1 transpose y. What I'm doing is each yi will be separately trying to become lower, correct? In other words, it will be moving in this direction, leftwards towards the origin. So negative yi will be moving in the rightward direction. So this range will be getting smaller, right? And this is the range of values for ax minus bi. What I'm doing is I have now defined 2 set of variables, x and y. Instead of just x, like here, I have x and y. I have removed the link, okay? And then I let ax minus b, the ith element of that, remain anywhere here. And I'm trying to push all the yi's inwards. Okay? And what will happen is this is equivalent to 2 inequality constraints, correct? This is one equality constraint, this is one equality constraint. It will reach, one of these will be active for each element I. One of these 2 would become active. So either when we reach the solution, x star is the optimum, either if it's less than 0, then negative yi equals ax star minus bi. Or if it's positive, then plus yi star equals ax star minus bi. Correct? But that's when we reach the optimum. Before that, we have two sets of variables now, x and y. Okay, so this is my constraint optimization problem. I'll show you an example to make it even clearer. So I'm trying to minimize with respect to x and y, 1 transpose y, subject to ax minus b. See, these are actually a pair of constraints. So ax minus b less than equal to y, and ax minus b greater than equal to negative y. And y is greater than equal to 0 because it's an absolute value. So this becomes a linear program, which will obtain the same optimum x as this unconstrained L1 norm minimization. Okay? Now, here is an example. I'm trying to minimize the L1 norm. Were we doing? Yeah, L1 norm of ax minus b. So this is what we want to minimize. Ax minus b equals this. So I'm trying to minimize this. This would be y1, this would be y2. Correct? And this is the linear programming problem equivalent. Minimize with respect to y1, y2, x1, x2, y1 plus y2. This is y1, this is y2, right? So that's what we want to minimize, subject to these constraints. So this ax minus b, the first element, will be between negative y1 and y1, and likewise the second element. Or breaking these into two separate inequality constraints, we have this. Okay, so what will happen is we have this constraint here, right? So from these two constraints, we get this figure. So y1, we're trying to minimize, right? So y1 and y2, y1 plus y2, we are trying to minimize. So y1 and y2, the algorithm is trying to push them closer to the origin. Okay, so this is what's happening. So this is the direction in which the algorithm is trying to move the y's. Okay. Now let's say, just think of it like this. Stepwise, we minimize with respect to x, then with respect to y, then x, then y, then x, then y. Okay, suppose we do that. So first, let's fix the x's. If the x's are fixed, 2x plus 2x1 plus 3x2 minus 3, this is this green dot here, and this is this green dot here. Okay, and now we will try to push the y's. So both will move simultaneously, right? The minus y1 and plus y1 both will move simultaneously closer to the origin. Likewise this. But they cannot go any, like this green dot here must lie in this region. So that's the limit. We cannot reduce y1 any further. Likewise, we have hit this green point here, so we cannot reduce y2 any further either. Are you guys with me? Okay, so
You just gave some values for x1 and x2.
yeah, and y1 and y2. I started off with some values, and then I just try to minimize with respect to the y's, keeping the x fixed. So these 2 points are fixed, the green points. And how far can I push the y's? Until they hit the green points, right? Because of these constraints. So we are here. Okay, it hit these points. So these now, next we'll try to adjust the x's to move these green points further inwards. Oh, sorry. Okay, so, oh, wrong figure. These bars should have been here. Sorry about that. So, well, anyway, from this figure, this figure is wrong. So now adjust x1, x2. Now we try to move the greens inward. Okay. But I think you get the idea of what's happening.
I couldn't get the last one here.
Oh, now once you see these bars, the y's are the bars and the green points are these. Okay. So once the y's hit the green dots, you cannot minimize with respect to y's any further. Then you try to adjust x1 and x2 so that these green points move closer to the origin.
But at first we specified the x1 and the x2 values.
Yeah, so we're stepwise, we're first trying to minimize with respect to the y's, then with respect to x. I'm just for explanation's sake. Okay. So that's how I'm trying to explain. It might be how the best way to explain it to you guys. Okay, so first minimize with respect to the y's, then with respect to the x's. Then when the x's are going to be, you're trying to minimize with respect to the x's, so the green points are going to move inwards towards the origin. Okay, so that's what I'm trying to say. So this is L1 norm minimization. L infinite norm. What's the infinite norm? Exactly, it's the maximum of the absolute values. So L infinite norm, it's actually a little easier than L1 norm. Okay, this is the problem. This is the ith element, and this is what we want to maximize. Max here, not summation. Previously it was summation I, now it's max I. Now when we had summation I, so we had different yi's. Okay, summation yi's is what we were trying to maximize, or excuse me, minimize. Now we can only have a single scalar y. So this is the L infinite norm. Y equals this max I. And this is the linear program. This is the figure. So all the green points will be populated here. There will be multiple green points, one for each of these constraints. You push the y's inwards, and then until it hits the first green. There'll be multiple green points. I don't have the slide, sorry. And then you adjust the x's to move the green points inward to make room for the y's. Now, I'll explain more in the Zoom. Dual LP. Okay, so you know primal and dual. Every primal problem has a dual. Is the dual of the dual the primal, by the way? Not always. If you have a COP, the dual of the dual is the primal, then it's called a self-dual. Okay, now let's look at what the dual of linear programming looks like. So this is the primal form of linear programming, right? Construct the Lagrangian. Now, this mu would be a little misleading because this mu corresponds to inequality constraints. I'm using lambda and mu for inequality constraints. Mu is not for equality constraints. Okay, unlike in my other lectures. Okay, so don't get confused. Both lambdas and mu's are Lagrange multipliers for inequality constraints. And they should always be, this is minimization, and so I have a negative here and a negative here because I have a greater than equal to here. That way, lambda and mu will be positive. Okay? Mukhtar, you seem confused, or
Yeah, I'm thinking about.
well, all you have to do is, let's look at x greater than equal to b. It's the same thing as negative ax plus b is less than equal to 0, or b minus ax equal to 0 is less than equal to 0. So it would have been plus lambda transpose b minus ax then, right? Instead of that, I've written this as ax minus b and put a negative sign here. That's all. Likewise for this, mu. Okay, and then what I do is I take all the terms that have x in them and put them together. So I have an x here, and this is independent of x. This is theta d, defined as the infimum with respect to x of this, the Lagrangian. Okay. Agreed? Which is, since lambda transpose b is independent of x, I can take it outside the infimum. So I have this expression here. What will this infimum be? See, this is you see all these transposes. So this is a row vector and x. Okay. What's the infimum? X is unrestricted now. We don't care. This, like you can make this infimum negative infinity, right? Agreed? So, except when this vector is all zeros. Okay, then no matter what values of x, this infimum will always be 0. Okay, so theta, this infimum becomes equal to, for all other cases, it's negative infinity, except when whatever is inside this is 0. So this vector should be 0. And in that case, the infimum is lambda transpose b. And remember that lambda and mu must be greater than equal to 0, because these are inequality constraints. Are you guys with me? So,
Why it should be minus infinity?
because we're trying to minimize infimum, we're trying to adjust x to minimize this expression here, or this expression here. How will you do that? Like, this set them to x is to plus infinity minus infinity, right? So that the infimum becomes infinity, negative infinity. Okay, so it's negative infinity otherwise, except when this inside is 0, in which case you cannot adjust x, it's fixed. It's lambda transpose b. Okay. So this is the expression what we have. And now what we want to do is, okay, we need to maximize this. Okay, I should have told you at the beginning that here, taking theta d is the minimum with respect to x, and then we maximize theta d with respect to lambda and mu. Okay, and that's the dual approach. The primal approach would have been to first maximize with respect to lambda and mu, and then minimize with respect to x, right? So we are switching the order of the max and the min. Okay, but when it doesn't matter when strong duality holds. Okay? Theta d star and theta p star are touching. Okay, strong duality does hold for this. You have the proof in the lecture notes. Okay, so since we want to maximize this, we will drop this case. We will try to maximize with respect to lambda and mu now, right? Lambda and mu are the variables, and we want to maximize theta d lambda mu. So we'll just ignore this case. Okay, so this condition must hold. What other conditions do we have? This. We want to have lambda and mu greater than or equal to 0. So I just took the transpose, so I have C minus A transpose lambda equals mu. And theta d of lambda mu is this then, under this condition. And mu must be greater than or equal to 0. If mu must be greater than or equal to 0, then C minus A transpose lambda must be greater than or equal to 0, correct? Now we want to formulate the dual. Okay, do we really need lambda and mu? We want to maximize this. Okay, now it's a function of only lambda here. Okay, and we have these constraints, lambda and mu, so this is what we want to maximize. And then I have this, let me put it as a constraint. And then lambda is greater than or equal to 0. I don't need the mu's. As long as, see, I would have, if I had introduced mu's here, maximized with respect to lambda and mu, nothing would have happened here. I would have had this constraint and lambda and mu greater than or equal to 0. That's all, right? But why do we need two sets of variables? Then we can just eliminate the mu. Okay, so this is what I have. Maximize with respect to lambda, B transpose lambda subject to A transpose lambda less than or equal to C, and lambda greater than or equal to 0. What does this look like? This is the primal. This is the dual. Okay, the dual is also a linear program. Okay, and what I've done, look at the difference, the x and the lambda. So what happens is the b got moved to the objective function, and the c got moved to the constraint. So since we know that strong duality holds, which one would you prefer to solve? It depends, right? Which of the dimensions of x and lambda. Okay. So this is the dual form. Okay?
So how did you got rid of the transpose?
Oh,
Yeah, over here.
I just took the transpose on both sides. I took this transpose of this side is C minus A transpose lambda and then mu here. Okay. Okay. Now, the good thing is let's interpret what the dual means. What does the lambda mean? Okay. We can gain some insights from linear programming. So this is, but I told you strong duality holds, so this is what you must remember. Now, you know that there are, what was it? No solutions, or if it's like unbounded, right? Degenerate cases. So what happens if this is unbounded? Or what happens when the primal is it doesn't have a solution? Okay, what happens to the dual? I won't prove this. So if the primal is unbounded, the dual is infeasible. So if this is unbounded, x can go to infinity, the solution, then the dual doesn't have a solution. Okay. On the other hand, if the primal is infeasible, if this doesn't have a solution, then the dual is unbounded. Okay, and if x star lambda star exists, then strong duality holds. Okay. Now we interpret the dual. I'll take up this example here. So I have this constraint optimization problem. Observe the coefficients here, okay? 9x1 plus 8x2, and here I have 1x1 plus 1x2 less than equal, greater than equal to 5. Well, I just took greater than equal to, just for this example. And 3x1 plus 2x2 greater than equal to 10. So this is my constraint optimization problem. Now, from these two constraints, I can form other constraints. I can multiply this by 1 and this by 1, and so I get this constraint. 1x1 and 3x1, so I have 4x1, 1x2 plus 2x2, so that's 3x2, and this greater than equal to 5 plus 10, that's 15. I can, the weights can be 2 and 1, right? So 2x1 plus 3x1 gets 5x1, and so this is, I get this constraint here. And I can get any number of other constraints. But mind you, I cannot, these weights can never be negative. Why? Because this greater than equal to would change, right? It would become a less than equal to if I have a negative. So these must be positives, these weights. And I can freely keep on forming constraints, new constraints, an infinite number of new constraints. Okay. Now, why should I be doing this? Okay. Now this new constraint, see this 4x1 plus 3x2 greater than equal to 15. Look at the coefficients. Here it's 9x1, here it's 4x1. We know that x1 and x2 are both positive, non-negative. And this is 8x2, this is 3x2. So 4x1 plus 3x2 greater than equal to 15 means that 9x1 plus 8x2 is also greater than equal to 15. So 15 is a lower bound of the objective function, right? So we don't know what's the minimum of the objective function. We're trying to minimize it. But we got some meaning. Okay, we know that the objective function, when we minimize it, we cannot go below 15. Now, this is from one of the new constraints that I got. How about this one? This says that it cannot go below 20. Now, which gives us better information? The first one or the second one? Second one, right? If we want to, the lower bound should be as tight, as high as possible. The upper bound should be as low as possible, right? The bounds must be tight. Okay. This, again, there's some combination of this and this gave me this, is an even better lower bound. Even better, right? But is this a lower bound? 150. I got this 152 in the previous slide. It's not, because here I have 40x1 and 30x2. You see that it exceeds 9 and 8, these coefficients here. So these will not serve as lower bounds. We must look at the coefficients. These coefficients of x1 and x2 must be less than equal to these coefficients here. Okay. So you get the idea. So now, let's call the weights lambda 1 and lambda 2. So this, in general, is how we try to find the lower bound. We take weights lambda 1 times the first constraint plus lambda 2 times the second constraint. And then we get this. I just took the all the terms containing x1 here. So lambda 1 plus 3 lambda 2 x1 plus this x2 greater than equal to 5 lambda 1. This lambda 1 times 5 and then lambda 2 times 10. 5 lambda 1 plus 10 lambda 2. So this, as long as lambda 1 and lambda 2 must be greater than equal to 0. That you know. Okay. So how do I tighten this? This is a lower bound. I would like to tighten it. Okay, so this is a lower bound of the objective function but it must satisfy what would be the constraints. This coefficient of x1 here can never exceed 9. This coefficient here of x2, lambda 1 plus twice lambda 2, can never exceed 8, right? So this, the coefficient of x1, I get this. And then I get this as my constraints. Okay, so these are my constraints. And now, what is the maximum lower bound? I want to maximize this. 5 lambda 1 plus 10 lambda 2. Okay, and these are my constraints. That's the objective function. So this is the primal, that's the dual. Okay. And you can see several things. You can see that looking at the lower bound, the dual, we're trying to, it's always lower than the primal, right? You can see from this. We're trying to maximize the lower bound. Okay, and this is exactly, if you use the expression that we derived earlier, you'll get exactly the same thing. It's exactly this form. This is the dual. Okay. Any questions anywhere? Okay, so sure.